very much for that introduction, Hans. And what I will do is, just to inform you, I will plug in a little clip on microphone, so I can't hear you immediately. So if you want to interact with me, you may just send a text chat. But then, as you said, I am trying to do an interactive session today. So when I'm expecting your participation, I will unplug the microphone so I can hear you. So I'm afraid I won't wait until the end to talk about myself. I'm not the kind of person who is polite, right? I will start with my self-introduction right at the beginning, because I believe that might make it a bit easier to understand why I'm choosing the focus in today's class. So as you said already, I'm an engineer by training, but I have always been interested in product design too. So when I finished my diploma degree and started working on my PhD, I concentrated on interactions between design and engineering, or engineering design and product design. And I also wrote my PhD thesis on this topic. So in the top right corner, you see a preview, unless it's covered by the video. So that was my research, that's my expertise, and it still is today. So I teach actual engineering design, and I used to teach it in Aachen until 2015, but I also teach industrial design for engineers, so at that interface. And I have actually been teaching that at Aachen with a Lehrauftrag, a special assignment, right until the beginning of this year. So I would travel to Germany over the new year for many reasons, of course, and then have the workshop phase of that industrial design class. And you see that little photo there. I will show you a big version of that in a minute. But as you said, now I am fully employed by the Thai University here, University King Mongkut University of Technology, and I'm working at the International Graduate College, which is called TGGS. And as you said already, it sounds a bit silly. I am the owner of this company. I use this wording of course, for legal reasons. And as you know, as you might know, in Thailand, you can only have one full job, so to speak, and I have a full job at university. And so I can't claim I am CEO of my company because in Thailand, you can only be CEO full-time, right? You cannot be a part-time CEO. So I'm just an owner. Of course, I am fully entitled to work for that company, but not full-time, so I can't be CEO. So you see a few previews here of projects, but I have larger images of these too. So this is already an older shot, but we do this similar group picture at my industrial design class in Aachen every year. And you will immediately see that there's a lot of Asian faces in there. Actually, about half of the people are from South Korea. And this is one special feature in this specific class, that it has always been a collaboration with Hongik University in Seoul. So every January, there's a group of 20 Korean students, design and engineering students, and their professor coming over. And the professor, you'll see him on the right-hand side, there's Sang-gal Hang. And I still very happy to work with him, not only in the university context, but also in actual design services. On the left-hand side, this taller gentleman than I am, this is Michael Lammel, by the way, and he's the owner of the Noah Design Company in Aachen. And they are important because they always give the design task to my students. So the point of this specific workshop here is there are 2 points. One is to work on a very realistic product design project on the one hand, and the other one is the international collaboration, really developing the skill to work in an international team. I think everybody who is with us now has learned through life that people, in fact, have different thinking patterns because of the different culture that they have been raised in. And this is an extra challenge for productive work, even if the work is only in a technical industrial context. So I'm really proud of this class. I've been doing this for more than 10 years, and I'm extremely happy to be teaching in Thailand now because it gives me opportunity to hone my international skills. And in the design field, as we'll discuss, this is not technical, but it's really much more about people and their thinking habits. So this is why I enjoy it. I have to say, the older I get, the longer I work, the more I'm interested in actual people and what is going on in their head and how to communicate properly, even if the context is creating value together in industry applications. So this is, as you can tell, I guess this is my university now. It's King Mongkut's University of Technology, North Bangkok. If you are in Thailand, you will certainly know the name. There are 3 King Mongkut's universities, and this one is near the Rama 7 Bridge. And my college, the International Sirindhorn TGGS, is actually the first building when you enter the campus from Pibun Songkran Road. And as you can see, the big bright red letters on that. This college was founded as a collaboration between Aachen University and KMUTNB. Actually, I think the contracts were signed in the mid-1990s already. And I was here for the first time in 2003 teaching a 2-week seminar or 10-week seminar, but that was just the pilot phase. Now, TGGS is an independent faculty within this university for 15 years now. We would have celebrated, if not for COVID, the 15th anniversary this year. And I am mostly teaching in the program of mechanical and automotive engineering in the major MESD, Mechanical Engineering Simulation and Design. Although I'm also teaching in the railway program that we have, the new joint program with Chulalongkorn University. And I'm also offering, no, I'm not offering, I have a design methodology course for all students in the electrical and software systems engineering program, which has been newly established. It's running for the 2nd time now. And I'm really proud of that because I didn't push myself into that, but it's actually this department that asked for that. So all the students have to take the course. This is why I can't say I'm offering it because the students don't have a choice. That is currently running too. Actually, next week will be the last week of teaching this semester, and the students will have to present the results of their 2nd design project. So this is something that I'm looking forward to. Now, my little company is a service provider in industrial design. I have a BOI promotion certificate for product design, and I also have a 2nd one in the production of musical instruments. So this is maybe one secondary effect. I am, of course, hoping to make more contacts. So if you ever consider taking or getting support with a design-related issue, I'd be very happy to hear from you, obviously, right? So maybe just to give you some information about the kind of projects, some examples that I have been doing on the side for industry. Maybe just quickly browse through that. That was the first one where I worked together with a designer in a professional setting 18 years ago or 19 years ago. The design office was NOAA, the same one that I mentioned. And at the time, they didn't have any 3D capabilities at all. So basically, I sat with a designer next to me for almost a year, and we developed this thing. We tested the prototypes right into mass production or serial production. This is a very expensive chair. It's around 800 euros nowadays. And I'm especially proud of that because you can still buy it. It's still in production. And 15 years later, the same company, through the same design office, contacted me again. The brand has been sold 2 times. The original engineering data got lost, which is great for me because I still had it. And I could basically sell the same design again because they needed to make a new set of tools because the old one is wearing out after more than 10 years of production. So here's just the view. So basically what we designed 18 years ago, what we engineered and designed was this mechanism, a very flexible, very high quality mechanism. And just recently, a 2nd series based on the same mechanism was launched. That is this collection S that basically has 3 chairs. I also did, let's say, in the formative years of my service provision, I did electronic consumer goods for a little company in Germany. This one, remote control for iPods at the time, was even awarded an IF award, but there's much more, and I'm just showing you some images as, let's say, background tapestry. This is more, what you're seeing now is more like an investment good. That's an acoustic camera, unit price around 180,000 euros if you want to buy one, for a company from Herzogenrath, which is near Aachen, and they were a leader in technical acoustics. So I did the complete design and even production through the workshop of the University Institute that is at RWTH Aachen. At the time, I was also responsible for their workshop. So basically, I took that job mainly to create work for the workshop. Yeah, that's a hobby project. You see that item already as the background image. I am a saxophone enthusiast. I always say if I win the lottery big time and I don't have to work anymore, I will definitely concentrate more on that. But this is one project where I combined my private passion and my professional passion, which is, of at least focus, which is the design, mass production ready design of plastic parts, which is where I get most of my orders nowadays still, because this is where industry loses a lot of money. Actually, there has been very little progress in the last 40 years. If you're a plastic engineer, you know the technology, right? But you're not a designer. And if you're a designer, typically you're not interested in getting into the details of how to properly design injection molded plastic parts. But that was one of the things I did pretty early on. And there's very good demand for such design services. So I would say the service that I'm offering is, number one, I'm able to work with designers. I am able technically to realize the shapes. I'm able to understand their language, and at the same time, I fully understand the whole technology, materials, tooling technology, and so on. So I can make sure that the parts, the product can be mass produced for minimum costs, but exactly the same quality that the designers are envisioning. An application field that I mostly focus on at university teaching is alternative mobility concepts. Although this racing bike you see here, that's a Paralympic racing bike, is not done through TGGS, although I finished most of the design while I was here. That was basically for a friend, a researcher at Aachen University, whose dream it was to start in the 2020 Paralympics in Japan, which obviously is not happening at the moment. A more recent industry project is in the field of furniture, HÄFELE. And this is a brand new system, Dresscode, a very complex system of parts. You can freely configure furniture, storage furniture, and this can be assembled completely without any tools. And I was very lucky to be involved with that. So that's a lot of components, more than 100 components that went through Lintale, but also the conceptual design, the very system design from the very beginning was supported by us. Although the leader design team is a Stuttgart German design office, Code to Design. Lintale likes to offer prototyping services. I very much like to do that. There's still a margin in there. And as you know, Thailand is a great country when it comes to sourcing stuff and production capabilities. That is one of the main, or one of the many reasons why I enjoy working here, is because you can realize stuff very quickly here in Thailand. This is an example project that is going through a university about smart mobility, about new mobility concepts. So let's start talking about the actual content today, and that is design methodology. 30 minutes as talking time is pretty short for me. You might have already realized I enjoy talking quite a lot, but I have 4 semesters worth of design related courses, so I can technically talk about design almost without repeating myself for weeks. I tried to focus on one very small specific aspect today, but before I do that, I want to give a broad overview of, let's say, the problems in the industrial context and even in the academic world when you actually talk about design. There's a general tendency to mystify design on the one hand, mostly by practitioners who want to be recognized as academics or theorists at the same time. And at the same time, it's being trivialized, especially by many industry representatives, but also many educational cultures. In Thailand, for example, as in most other countries in the world, design itself within engineering is not recognized as an expertise at all. Even after 6 years, I haven't found anyone else in Thailand teaching engineering design methodology on university level. Of course, there's product design here. There's a lot of great designers in Thailand, but it's not an academic field. Now, when I talk about trivialize, I'm also talking about many new approaches trying to market design skills. Obviously you can guess what I'm talking about when I'm saying design is thinking. It doesn't, in my view, it's clever marketing, but it's not helpful to communicate that you can teach design methodology in a 1 week or 2 week course. Because everyone who is actually designing realizes that this is a lifelong learning process. And even if you just try to grasp the underlying theoretical concepts, it will take you a long time of studying, applying, and understanding to really use the concepts in a productive way. From the industry standpoint, the problem with the fact that design is not really about technology, but mostly about thinking. Thinking does take time, which is often overlooked. And at the same time, thinking itself doesn't show its progress, right? Everybody who is designing, actually everybody who is regularly tackling tasks and problems knows that thinking just takes time. And it happens, it's not very plannable. It's not always plannable. So sometimes after weeks, you have solved a problem in your head and it's not there. You then have to document it. And many decision takers in the industry confuse the documents that describe a design with the actual work, with the actual value creation and the actual activity, right? The other thing is, as I said too, and this is mirrored in many educational systems, is that design is often not considered to be expert work at all. In the engineering context, there seems to be the belief that if you have an engineering degree in any field, you automatically are able and capable of designing a technical system. Let's say if you study production engineering, people expect that you can design a production machine. If you concentrate on materials engineering or plastics engineering, people expect you can design plastic parts, and so on and so on. And this is what causes a lot of problems, is that discrepancy in how decision takers in industry and even educational systems see design. The other problem is, and I recognize that when I communicate with industry, is that obviously the word design is claimed by a lot of people. There are lots of different types of design, and the terminology is not clear. In engineering, which is about technology, which basically is applied science, the concepts are very clear and universally international. Sometimes they might use a different word for a parameter that has some sort of cultural national background, like Young's modulus is a module. So sometimes technical parameters are connected with names, but this is a national thing. But generally, everything in engineering, it doesn't matter where you study or where you perform, that is the same thing. But design, even engineering design, is a highly cultural thing. And everybody likes to promote their own terminology. And even the industrial sectors in different countries use their own terminology. So if you're not really an expert, it is very misty, cloudy, and unclear. If I just talk about product design, the Americans like to call it styling, for example. But if you say the word styling to a German designer, he will probably start a fist fight with you, because styling is considered to be a bad word for German product designers. So that, of course, has to do with a big problem when in the industrial design in the industrial context, because of all this complexity and lack of clarity, it is very difficult for most industry representatives to really deal with design. For example, create design competence in-house, or even start using external designer service providers. So I'll talk briefly about that. One way of looking at the two main different design domains, which would be engineering design or technical design, and product design or industrial design or styling or whatever, is actually looking at the items, or looking at the look at the items that are being designed. Now, engineering design is about creating technical systems that serve a purpose. And as we will see in the technical context, this term purpose has a very narrow definition. It is about transforming an energy, material, or signal flow. Now, there are many items that have such purpose, but they obviously have other values too. And as you see on this watch, this is an expensive watch, and a lot of people are ready to pay an awful lot of money, even if the timekeeping qualities of this watch are not so much superior from many other brands that are much cheaper. So obviously there's a larger scope of value in them, and that can also be described in a functional way. And this is a very satisfying way of showing how the scope is larger when product design is involved. Now, this thing would still be a thing that serves a purpose, but it also can create an emotionally positive experience while it's being used, and it makes the owner more satisfied. So if you look at things, the design of things in that scope, that will include the domain and expertise of product design on top of engineering design. So that brings us a bit closer to a more specific definition of this value chain, of this process of design. And personally, I have been using this wording to describe the different design phases, which make design plannable, measurable, and therefore you can control the quality of the design process a lot better. So I look at design as this process or business process that is actually leading into production, which is not always the case, but this is typically the context that I work in and that industry is interested in. You consider design if you are interested in producing and selling these goods. So the last phase before production actually starts is design engineering or engineering design. And designers actually often just call it engineering. And I will focus a bit on methods of that, because I believe these are methods that are really interesting, easy to learn, and easy to apply. Before that, we would have the more complex design phases that are actually not about problem solving as much as design engineering is. And I differentiate two different phases here, which are called experience design as the very front end. And then the second phase would be interface design. With interface design, I mean the actual design of objects and every other interface. So for example, graphical design, app design, website design, even if it's not three-dimensional physical objects, that would be included in interface design. And we will not talk anymore about this today. Same as experience design, I have a whole, that would be a whole semester of dealing with that. Experience design would actually be the very valuable first phase of any project that would be started by a producing company that doesn't know what their next products will be. And you can generally say that established companies that are able to stay successful by keeping on bringing new products or new versions of their established product into the market, they are successful because they have managed to include experience design in their processes. Now this structure here, each of these boxes can be detailed to very great degree, of course, and need to be detailed if you're interested in using it. But as I said, this overall macro structure is really useful to communicate upcoming design projects, for example. Now, I'm not sure if you can see everything. Sometimes I have to push my little windows around. So this talk is called Design Methodology, and I quite often get the question, what actually is a design method? How does that relate to a design process and so on? So I have a very simple way of putting it. A design method is a method for the brain. It is a tool that supports applied thinking. When I say applied thinking, I mean it's thinking in the professional context that is part of this value creating process. When I put the hammer there to make the analogy, this is how I try to explain to my students that really you can design without design methodology. You can even be a successful designer. You might even be, if you're lucky, a very efficient designer because most of the work is actually done by the brain. And the purpose of the design method is just to make that process more efficient. And like with a hand tool, like a hammer, for example, normally we can use these hands for quite a lot of activities, but there are a lot of activities that we can carry out in a much more effective and efficient ways if we use the proper tool. Now, what is a methodology? A methodology is generally a collection of methods. So if you use that analogy of tools for the brain, then a methodology would be a toolbox for the brain or a toolbox for applied thinking. This is also how design methodology is taught. There are some macro tools, like, for example, the overall design process. And then there are such tools or methods that are used in a very specific context to support, for example, a design step within the design process. What is normal for a toolbox is that you will take it to any job, but you should not expect to be able to use all the tools for every job. And the same is true about design methodology. And this is hard to understand for students, for example, if you introduce them to design methodology. They often believe that they have to apply all the tools in the toolbox on any project. And there's almost no project that requires all possible tools. So again, this is why I think this analogy is really useful to understand how you apply design methodology. In the introduction or in the announcement of this little talk, I did mention that Germany has a history of recognizing the importance of design methodology. And I just talked about that with Hans before we started. You could say the 1950s, 1960s in Europe, there were a lot of people talking about design methodology. That was, you could say, zeitgeist, spirit of the time. But not a lot of governments actually recognized that this is useful to promote, to fund. And the German government at the time, they really realized that Germany as a country, as an economy, needs to put as much effort as possible into Germany's potential to develop new designs, innovations, new products. Sorry about that, I need a sip of water. So even if this concept of design methodology was discussed in many countries, I need a spray for my cough too, hang on. Wonderful. Not all the countries actually invested money in that, but Germany did. So a lot of new chairs were called specifically for design engineering methodology. Most major German technical universities have a dedicated chair of design methodology Konstruktionslehre, Konstruktionsmethodik, or something like that. And in the 1970s, groups of these experts came together to author the first version of a VDI guideline. VDI is the Verein Deutscher Ingenieure, something like the German Association of Mechanical Engineers. And that created a document, a state of the art in design thinking. So companies were actually able to apply these guidelines, and therefore, for example, in case of liability issues, they could prove that they actually designed according to the state of the art. And I have to say, not all the companies do that. And even in Germany, many people still dispute the value of, let's say, this specific diagram here. Now, this diagram I would consider a macro tool, a macro method, because it describes the overall process. But then there will be a lot of tools that are specifically applicable in each of these phases. For example, you see phase 1, specification phase, and there's a lot of methods to support that. We'll discuss one of these, for example, analyzing problems, setting up specifications, identifying requirements, processing requirements, just generally requirement management, and so on. And then we proceed through this process, conceptual design, and then later embodiment design. And there are endless numbers of very specific methods that can be used here. Just to make the point that this is really part of the German engineering culture, or it has become, there's a lot of VDI guidelines, not only the very basic one that I mentioned before. You will see design, you will see industrial design, you will see design of mechatronic products, you will see a guideline on ergonomic design, and so on and so on. Now, what is the general strategy of engineering design that I want to discuss today? I like to claim that basically the challenge of engineering design is the challenge of managing complexity. And this is completely unrecognized by a lot of people, and this is what causes actual problems with design. A design process or any design is not fully determined, like, let's say, a scientific problem that can be described by a limited number of formula. In design, there are so many degrees of freedom that require a lot of decision taking. The funny thing is, a lot of these decisions are very simple decisions. For example, the geometry of technical parts is only to a small degree really determined by its functions. There are still a lot of degrees of freedom where there is no technical argumentation, or at least no technical argumentation that can be easily recognized. And this is really what challenges people. This amount of freedom, so to speak, this enormous complexity intimidates people who might be highly skilled and knowledgeable as engineers, but if they don't have any practice at this design process, it will even psychologically, mentally run them down. And then most, let's say, non-expert practitioners, they just switch the mode to using pure intuition, even if they were trained to usually use science and math to justify any decision. But in this case, they just completely switch to intuition. And what I mean by that is what many people just call experience. So they will choose a concept because they have done like that before. And you can immediately recognize that will be an inhibitor of innovation. People are trained like animals to make quick decisions, almost in an effect, almost in a reflex based on a situation. And for animals, that saves life, right? Let's say you're a little animal that can easily be eaten by a big a predator. Now the little animal will quickly choose, without analyzing the situation, what to do, right? Based on reflexes. And the weird thing is that a lot of professionals design the same way. They perform what I call squirrel design. As soon as they come into this situation, they for various reasons, will quickly choose an initial solution and try to push that through. And many reasons for that are also based on pressure. Design is a process that is under time constraints and money constraints. And you can actually see that with a lot of practitioners in design, that they really fall into some sort of panic, into a mental panic when confronted with the design situation. Just yesterday, I had 3 design teams from my machine design process class present their results of their first ever engineering design project. And it would have been great to film it and analyze it. You could definitely see, because of the time constraints that I put them under, they just panic. And even if they have been learning all these principles and methods before. And the funny thing is, or the satisfying thing is, they will recognize that. If we went right into a discussion after their presentation, and after the pressure falls off their brains, they actually realize what they should have done, how they should have reacted. Now, design methodology, the main purpose is to avoid squirrel design. And it's about avoiding intuition, because intuition might be great if you're lucky, but in many cases, intuition will put you on a wrong path, wasting a lot of time and concentrating your time and resources on a technical concept that will just not be the perfect solution or the optimal solution for that specific design problem. And I always have to make that point. We're talking about industrial context where time and investments will decide on the fate of a company. So it is really necessary for a company to embrace these concepts to ensure the quality of the design process, as they naturally do in, let's say, in production. There will be quality assurance in production, but often in design you don't find that. Now, how does the most general approach in engineering design work? It's a very simple concept if you analyze it. The idea is to find the best possible concepts by considering all possible concepts. Now, how do you do that? How do you consider all possible concepts? There is another strategy here. The idea is you will break down the overall problem into granular problems, into simple problems, because it's much easier to solve simple problems than a complex problem. And then you simply have to find all possible solutions for each subproblem or granular problem. And there's this underlying axiom that it is actually possible to then recombine the solutions for each of the subproblems, and it will form an overall concept. Okay, so we're not talking about CAD design. We're really talking about conceptual design before you actually start working on the CAD. And talking about squirrel design again, another symptom of squirrel design is if designers quickly start working on their CAD, because they feel under pressure to present something to the customer or to your boss or whatever. And with conceptual design, it just doesn't produce the sort of images that seem to be very impressive. But the message is here, if you follow this approach, you will have a sustainable process. So what you see on the right hand is just a very, very brief summary of what we're doing. We're starting with a purpose definition. My God, I'm very slow. And a specification of the topic. Then we'll break down that overall job. Then we'll identify all possible principal solutions for each problem, and we'll recombine them, as you see here in this morphological matrix. And then we'll evaluate in a balanced evaluation. So that was my layout, but we come to the interactive part. I have two or three, actually I have two interactive examples here and one final example of pointing out how anyone can really make use of the basic concepts. And it's much like meditation. Everybody's brain is able to do that, but it's against the habits you have in thinking, and it's a bit more difficult to apply these when you're under pressure. So let's try to do that. So three methods. The first one would be solution neutral purpose definition, and the second one will be more generalized thinking in functions. And then at the end, I'll demonstrate one way of actually identifying more solutions to a given problem. So what is solution neutral purpose definition? It's very basic. It's the very first step of any problem solving process, especially in design, would be to try to define the purpose of the technical system that we're trying to design. And what is important here is that this definition must be free of any solution. We must be careful not to include any experience, any knowledge that we might have of how this purpose is being fulfilled. Just define the purpose. And this purpose is actually the same as the overall function. And as in math, a function is described by input, operator, output. So a technical system is something that will put something into and something will come out. And what will come out is normally different than what we put in. And this transformation from input to output, that is the actual purpose. And the word technical function or overall function means the same. When we do that, we realize a technical system can only have three kinds of flows. That would be a material flow or an energy flow or a signal flow. And any system that you can't describe as such flow is not really the domain of engineering design. There's one neat game that you can play to make that exercise more satisfying, and that is to classify technical systems according to the kind of flow. So on the left, you see obviously an engine. Now, if you try to come up with the purpose of an engine, well, one might say, well, it's about burning fuel. That would be material flow. No, that's not the purpose. The purpose is to actually get energy. What we want to have is mechanical energy, torque, and rotation. And we achieve that by getting this energy out of fuel. So the purpose of an engine would be to transform the chemical energy in this combustible fuel into mechanical energy. And we just agree on a new rule that we call such energy transforming systems, technical systems, we call them machines. An engine is a machine. Okay, so from now on, if you have an artificial system and technical system with the main purpose of transforming energy, we can call that a machine. Now, the second thing, most people call that a coffee machine. But if you think about it, what coffee does, it's about making a drink. A drink is material. So we can't call it a machine by these new rules. And we decided to call it apparatus, even if that word sounds kind of awkward. Now, the last kind of flow would be a signal flow. Normally in an interactive way, I would ask you what you would interactive. Would anyone like to tell me how we should generally call technical systems that have the main purpose of transforming signals? Any idea? Does anyone want to comment on that? You can.
A tool?
No, a tool, that would be too general again. So a machine is an energy transformer. What would you call your phone as a technical item? Or a fax machine?
Device?
Exactly, you got it. That was quick. Thanks. That's 5 points for you, Mark. So yeah, let's call that a device. So here's some interactive games for everyone. We have 3 points to give out, or maybe we can. We have a new guest here. So you can tell what this is. These are solar panels or solar cells. What is the main purpose, and how would you classify this technical system? Anyone? Just, it's open mic. Just scream if you have an idea.
Energy?
It's an energy flow, right? So what's the purpose of a solar cell? You have to word it explicitly. That's part of the game, to really input, operator, output.
Then it's a machine.
It's a machine, that's sure. It's about energy. So you would have to, in this exercise, you would have to write down the purpose is to transform sunlight into electricity. Okay, so that's energy flow. So it's a machine. What about this? Air conditioner. Well, air conditioner has the word air inside. What is the purpose of that technical system? What is the main flow? What is the classification?
would say apparatus to cool air?
Absolutely. I would say so too. Now, many engineers, especially if they know too much, they will recognize that this is a system that needs quite a lot of energy, and heat is energy. So they might say it's an energy transforming system, and it's not completely wrong. But on the other hand, this is a meditation on something. I would still argue that the air is the most important aspect, because an air conditioner is not about cooling a room, it's about cooling the air. If you subtract air from air conditioner, then you don't serve the purpose anymore. So again, this is an interesting discussion here. And the result is not as important as the process of discussing it, that this is a system that is handling air. And it's changing the properties of this air, temperature, it even takes out the humidity. And these considerations are important because they often lead you back to the right track. Engineers often get lost solving sub-problems, technical problems, that are often not really about the main purpose, but really subsystems, right? So this is a good concentration exercise. What about this one? What is the purpose and therefore the mainstream or the main flow and therefore the classification of this thing? Anyone? We have points to give away. Anyone wants to take a guess? James, are you still there? Come on, James, give it a go. Don't be shy. No? Okay. So, well, this is a forklift. Most engineers would say, well, this is about energy because we are lifting objects up and therefore they have more potential energy than before. We do have a chat, but I don't know. So I have answers here, but I don't really have no answer to what. Again, that would be an engineering pitfall here. Basically, what we're looking at is something that you use in warehousing, right? So it's really, we need to lift the objects up simply because we don't have enough space to put them on the floor. So really, this is about materials handling. So this would be considered an apparatus, even if it uses a lot of energy. What else do we have? There's one more, my favorite. This is what is always used to confuse the students. What is the purpose and classification of this? It's a typewriter. Last one. Oh my God.
Yeah, it's giving signals, so it's a device.
Very, very, very good. Now, many students, they say, well, this is about putting ink to paper, so it's an apparatus. But this would not be solution neutral, right? You are right. The purpose is to save a text, right? To save a text. And at this time, this was the best technology we had, right? Is putting ink to paper. But by the purpose, this is a device. And if you just think about paper and ink, you will never make the transition to computers and word processors or whatever other technologies you can use to save text. So that is the nice first exercise here, is to consider the overall function and to classify a system. Now the next phase we have to go through is to break this overall purpose definition down into many smaller problems. And I don't think we have that much time to discuss it. What design methodology has here is like closed systems of functions you can use. So basically, when you know the input and you know the output, you can break the overall function down into elementary functions. And the system even gives you catalogs of all existing knowledge that can be used to solve specific functions. So in accordance to what we heard before, there is such catalog for energy functions, there's such catalog for material functions. And when you realize some systems have to connect energy and material, then there are also these connecting building blocks. And signal functions we don't need to discuss because technical systems always use energy or material. So in order to practice that, and that normally requires time, two of my favorite examples would be the brake of any vehicle. and actually a coffee maker too, right? So let us briefly consider the function structure of a brake. So even just the overall purpose to describe that in an abstract way by using functions without using our knowledge of how brakes work, that is quite a big step. And the way to do that is to really consider what is the input of the system, what is the output of the system. So would anyone like to make a suggestion on what is the input and what is the output of a system that we call a brake? And that is the same discussion as the purpose that we had before. Now, what do we have before we apply the brake? What do we want to have after we apply the brake?
Reducing speed.
Mark, you're the Rethink Business Award winner, so you go first.
Reducing speed.
Again, we need to have something at the input and output or before and after state. So we don't want to have speed unless we want to buy a substance, right? And what in this case, this is not specific enough.
Okay.
And it's trivial. This is the problem because it's so trivial. Really, we're discussing changing our thinking patterns here. So please don't be mad at me for discussing this triviality, but this is the whole point.
I would say movement or movements with a resistance. Adding resistance.
So resistance would already be would not be solution neutral. You are considering a solution to the problem when you say resistance. No, it's much simpler. The input or the state before. Now we have a chat answer here. This is cool. Mr. Supik says changing kinetic energy into heat energy. And Mark says to transform energy. Now, these are both wrong answers from people who know too much, right? So the actual answer would be, the input is a fast car, the output is a slower car. This is what we want. So we don't want to transform energy at all. This is very important that we realize what do we want and then we separate this from our thinking about how we can achieve it. So again, the input would be a fast car, the output would be a slower car, maybe even a stopped car. Okay, now the next step would be to analyze, is the sum of the inputs equal to the sum of the outputs? Now, if you have a fast car as the input and a slow car as the output, you will realize, no, this is not equal. The mass of the car will be the same, but if we balance the energy, there's something missing. So the output must be energy. I'm wondering if I can actually make a sketch here. So what you would do here is you would start describing this system as a black box. Input would be, I have to use abbreviations, fast car, FC. Output would be a slow car, SC. And this is not balanced with regards to the energy. So obviously we have energy coming out, right? And this actually is the purpose of a brake. We want to separate the energy from the car. We don't want to transform the energy. Now that's interesting to realize. Now suddenly we realize by just balancing that, we suddenly have energy in abundance. Now we can think about what we want to do with it. But please forget everything you know about how it's done. So if you realize you have energy, you would say, wow, that's great. Actually, before I had kinetic energy, why don't I just save kinetic energy? And then if I want to accelerate the car afterwards, I can do that. I just have to save the kinetic energy somewhere, or the energy. So let's put a symbol for insulation saving there. This is actually our ideal purpose description. We subtract kinetic energy from the moving car and we store the kinetic energy. And then if we want to accelerate the car, we can use it. And that is what we're trying to do. We're trying to free our mind from how it's done. Now, the problem with saving kinetic energy is it's very difficult to do. This is another thing that I go through with my workshops. Please give me a concept design of how to save that kinetic energy. Most younger students realize it's not possible. Or actually they don't even think about it, but they just transform this energy. So some will say friction, and they say, sorry, no, this is not. This is how you change kinetic energy into a different energy that is easier to dissipate, right? But actually, you could use a flywheel. You could have a heavy rotating disc in your car, and it's technically possible to take the energy from the moving car, store it in the fly disc, and if you have a complex system of clutches, you could actually, to some degree, accelerate your car again. But then the fly disc has many disadvantages. It's heavy, you have the gyro effect, meaning you can't steer your car freely anymore once it starts rotating and so on. And this is where your thinking starts. What auxiliary functions could I realize? For example, nowadays people will quickly think about recuperating brakes. They will say, okay, I could put a change operation in here, change the kind of energy. I will change kinetic energy to electric energy, and electric energy I can store on a battery. Great, we just made an invention. We moved away from the friction brake. What is interesting too is if we calculate the amount of current that we need here, is we will find out, oh my God, we have a very high current. Even if we're not discussing technical details, energy principles already apply here. So you can you will realize the amount of energy within the time. And this is a great way of understanding why disc brakes, for example, are designed the way they are. It is because of the speed of heat transfer. Because actually we don't want to heat our brake up. We want the heat to dissipate into the environment. But it is simply technically not possible to release so much heat immediately. So what we do is we heat up a piece of steel. This is possible to do very quickly, and then the piece of steel will cool down very slowly. Okay, because we're running out of time, I can't really consider that, but I hope I have whetted your appetite for this kind of thinking. This is one of the key techniques to start innovation. Coffee maker, another beautiful example that we don't have the time for. So the last thing I will discuss, and I use more than the time I have, would be this little example of how we can actually identify more solutions. In design methodology, as I said, it's a toolbox. All approaches to finding solutions are allowed, even heuristic methods. So even brainstorming is considered here under. And the approach is just to find all solutions so we can choose later. There's another approach called systematic variations, which is very useful to identify design parameters, and then systematically vary design parameters. And then we can use the design parameters to create classification schemes which show us blatantly what are the solutions that haven't been invented yet. This is a very powerful tool really to enforce new solutions, to really identify solutions that have not yet been realized. And one little example that I always use with the students, and this is really the last thing that I want to show, is a good old-fashioned Motorola Razr phone, where we consider the folding of the phone to be a working motion. Now we just need to identify the parameters that describe the motion, and you will find that it's the kind of motion, which can be a rotation or a translation or a combination, and the direction. This is a good exercise for the students. We use two parameters, kind of a motion and direction of motion. So we have two parameters that gives us a two-dimensional space, a two-dimensional table, and we now need to identify all possible values of these parameters. So for the kind of motion, that will be translation, rotation, or combination. And for the direction, that would be X, Y, and Z. So we have 6 or 9 free fields. We can now systematically, with this scheme, identify possible configurations of phones, and very logically. And this was, if we're old enough to remember flip phones, most of my new students they just know these boring things which have no working motion at all. They will actually be able to systematically develop everything. And at the time this was done. So instead of just a folding phone, there was the sliding phone that changes the kind of motion. You can change the direction of this systematically. You will get a different direction of sliding it open. And if you stay with the rotation that the original phone had, but instead of using the x-axis, take the z-axis, you will come up with this weird phone that I honestly didn't believe existed. But Motorola, in their panic, developed even that one, hoping that people would see a purpose in that. And the third axis of rotation is this one. Nokia did that too, but as this completely didn't make any sense for the normal function, screensaver and so on, they came up with a phone that needs a MP3 or camera mode, MP3 player at normal mode, and so on and so on. So that was this last little example that I wanted to show, which should demonstrate really that design methodology is about changing your thinking patterns, trying to distance yourself from only using your intuition, or what I call squirrel design. Now I've finally reached the end. I'm so sorry that I've used a lot more time. You might still be interested in asking a question or discussing a point.
I'm sure the audience is. Thank you, Alex. It's 1 hour and 6 minutes, so it's still very nice in the time limits. You said thinking and how you look at, let's say, items. I will definitely look differently at my air conditioning unit and in the morning when I make my tea coffee apparatus. So thank you for sharing that knowledge with us. Indeed, we have some time for a burning question. If the audience would like to ask a question, please unmute yourself, both microphone and camera, and you have an opportunity to ask directly to Alex.
We have a user called Man V who asked, where can I study this by myself? Well, actually, I think I didn't make the point exactly. A design methodology is there are a lot of different people who want to promote their own way of discussing it. The good way is there's a lot of free approaches available. If you want to study this specific school of design methodology, there is a textbook available from the authors Pahl and Beitz, which is the best-selling and most recognized book on design methodology worldwide. This is originally a German book, and actually on the 7th German edition, I wrote 3 chapters of that. But the English editions, they're a bit behind. So I don't know if it's still the 3rd edition, and that's translated by a professor called Lucien Blessing in Springer. You will find that in Springer. So that specific school, you'll find many aspects of that if you want to read a book. However, it's like meditation, right? I'm serious about this point, right? So you can read a book about meditation, but not a lot of people will manage to learn actual meditation just after reading a book on it. It's very difficult to change your thinking patterns without someone who will discuss that with you. So if there's actual demand, I have done these workshops at universities for free, right? If I would get enough requests for me to justify a workshop, I would be happy to organize one at TGGS, W entered, whoever that is, if you are in Bangkok, for example, right? Or you just do it with friends. You could go through, I think, do we publish this presentation or the video?
Yeah, actually we do. And maybe I can make a recommendation, Alex, and also to you, I think it's Manu. Coming Tuesday, Alex, you're invited to join us in the session, which is on the 1st of December. We're going to have an interesting physical session, like you said, is sharing of ideas in a physical way. So more than happy to continue this conversation on a live basis with you and all the other guests, so we can also thank you properly with probably a glass of alcoholic beverages. Yeah, is that a good way to start?
That sounds perfect.
Then I would like to say thank you to you, Alex, in particular, but of course also to the audience. We started with 21, we ended up with 18 participants, so well done. That's a big compliment also, Alex. Thank you for providing your knowledge with us. Mark, thank you for asking questions. I wouldn't expect anything less from, of course, a winner of the recent award dinner. So thank you for participating. Martijn, again, also thanks for your contribution and making this possible. I mentioned already the 1st of December will be another busy, eventful day for the NTCC. Everybody is more than welcome to come to this bar zoo, which is underneath Sheraton Grand near Asok. We'll start from 5:30 with some interesting, hopefully, topic discussions, sector review 2020, but then fast forward into 2021. How do we see certain sectors, certain industries moving forward in this current challenging business environment? We do that together with our Belu Thai friends. So Mark, I'm sure you will be there as well. And our British Chamber friends will participate as well. We'll end the evening with some light entertainment and casual drinks. So it's going to be probably a late night as well on this coming Tuesday. And on a more serious note, we'll conduct another webinar, which will be on the 17th of December for everybody who's interested in the concept of service design. Now, that's completely different than what we heard today, but nevertheless more interesting as well. So we'll continue in these webinar sessions and we'll communicate as always via LinkedIn, Facebook, and direct emails. We have recorded this session. We will upload this tomorrow, probably on LinkedIn and Facebook. So if you would like to see this, then you're more than happy to join. And if anybody would like to be in direct contact with Alex, either next Tuesday or by email, more than happy to connect you, because that's the purpose of the Netherlands Thai Chamber of Commerce. I wish you all a pleasant evening. Thank you for participating again, Alex. Thank you for your time. And,
thank you for your
all right. And I'll say nice evening and see you all soon. Bye-bye.
Bye-bye. Thanks for your nice feedback, dear attendees. It was a pleasure to be here for you.
Good, good, good. Bye-bye. Have a nice evening.